Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll be discussing the angle addition axiom and the linear pair theorem. This video was produced for Ohio University Math 3110-5110 College Geometry. The reading for this video is from section 5.3 in the book Geometry, a Metric Approach with Models by Millman Parker. Now, as I just said, the main topic for the video is the angle addition axiom and the linear pair theorem. But actually, we'll start by talking about the angle addition axiom and what it tells us about statements about points in the interior of angles and big and small angle measures. And then we'll talk about the linear pair theorem. And then we'll talk about some converse statements that are also theorems. Let's recall some useful theorems from section 4.4. Now, these were rather hard to prove. I forget if we actually proved these in a video. They're proven in the book, some of them. But at the time that they're introduced in the book, they have kind of a vague statement saying this kind of theorem will be useful in the future. But then they don't really say much about that. And in fact, when they get around to using these theorems in the current section, 5.3, they don't always cite them. So the first theorem is Theorem 4.4.8. It says, in a past geometry, if points C and P are on the same side of a line AB, then P is in the interior of an angle ABC if and only if A and C are on opposite sides of line BP. Now, I prefer an alternate wording for this theorem. Given points C and P on the same side of line AB in a past geometry, the following statements are equivalent. That is, they're either both true or they're both false. Statement 1 is P and A are on the same side of line BC. Statement 2 is A and C are on opposite sides of line BP. Now, it'll be helpful to make an illustration of this. So let's see if we can illustrate statement 1. So it's statement 1 along with this given information. All right, so in the left drawing, I've illustrated this statement. P and A are on the same side of line BC. In the right drawing, I've illustrated the second statement. A and C are on opposite sides of line BP. So that's not an easy theorem to prove. It's not terribly difficult. I don't remember if we proved it back in video 4.4, but it's a standard application of section 4.4 techniques using the plane separation axiom to prove statements about points being on the same or different sides of a line. Another theorem from section 4.4 that's useful is 4.4.9. It says, in a past geometry, if B is between A and D, then P is in the interior of angle ABC if and only if C is in the interior of angle DBP. And I prefer this alternate wording in the form of an equivalence theorem. It says this, in a past geometry, given points ABD such that B is between A and D, the following two statements are equivalent. Statement 1 is P is in the interior of angle ABC. Statement 2 is C is in the interior of angle DBP. So I'll make an illustration of those two statements. So on the left, I have a drawing of statement 1. P is in the interior of angle ABC. On the right, I have a drawing of statement 2. C is in the interior of angle DBP. Now recall the definition of angle measure from section 3.1 to say that we have an angle measure based on R0 means that we have a past geometry and R0 is a fixed positive number, and it means that we have a function called m that eats as input angles and spits out as output real numbers and that function satisfies these three properties that are called the axioms of angle measure. First axiom says that the measure of an angle is always greater than 0 and less than r0. The second axiom, called the angle construction axiom, says this: given a half plane h, a ray on the edge of that half plane, and a number theta between 0 and r0, given all that stuff, there exists a unique ray BA with A and H such that the measure of angle ABC is that number theta. I kind of raced through that, but we'll slow down and visualize that when it comes up during today's video. The third axiom of angle measure is called the angle addition axiom. It says that angle measure is additive in the following sense. If a point D is in the interior of an angle ABC, then the angles add up in the following sense. The measures of the two angles that are created by point D add up to the measure of the original angle ABC. And recall the definition of protractor geometry from section 5.1. A protractor geometry is just simply a past geometry with an added feature of an angle measure that works. So this collection of four things where these three things are a past geometry and M is an angle measure that works for that past geometry. Now I'll discuss section 5.3 in two videos. The section is titled Perpendicularity and Angle Congruence, but those topics will be taken up in the second of the two videos. In this video, we'll discuss some important consequences of angle measure axiom 3, the angle addition axiom. Now first I'm going to talk about statements about points in the interior of angles and big and small angle measures. Now recall that angle measure axiom 3, the angle addition axiom, says that if D is in the interior of angle ABC, then those angles add up in that sense. There's an illustration of the angle addition axiom. If D is in the interior of angle ABC, then the measures of those angles add up. Now, because we know that the measure of angle DBC is positive by the angle measure addition axiom 1, this automatically gives us the following weaker statement. So since this green thing plus that blue positive thing equals this red thing, we know that that green thing has to be smaller than the red thing. The measure of angle ABD has to be smaller than the measure of angle ABC. So there's an unstated corollary that says this: if D is in the interior of angle ABC, then these angles have that big and small relationship. Now this is the first time I've used that kind of wording of big and small, so I'm going to make a drawing to illustrate how I would convey that visually. Now I'm going to use the same drawing and modify it slightly. So there's an illustration of this unstated corollary. Now you can see that it's a weaker statement. This drawing doesn't make as strong a claim as this drawing. This drawing up here actually says exactly how the angles add up precisely. The bottom drawing just simply says, well, one's bigger, one's smaller. Now remember that when a theorem has the form of a conditional statement, the contrapositive statement is automatically true, and it's not a separate theorem. So the contrapositive of that unstated corollary is this: if the measure of angle ABD is not less than the measure of angle ABC, then D is not in the interior of that angle. But again, that's not a separate theorem. That's just true automatically because this is true. And this is such a obvious seeming statement that the book doesn't even present this as a theorem or a corollary. But remember that when a theorem has the form of a conditional statement, the converse statement is not automatically true. If the converse statement is true, then it constitutes a separate theorem and it has to be proved. It turns out that the converse of that unstated corollary is true. and its proof is not so simple. So the unstated corollary had a very simple proof. It was so simple that the corollary wasn't even stated. But the converse statement is true, and its proof is not simple, and so it's presented as a theorem in the book. Theorem 5.3.1 says, in a protractor geometry, given points C and D in the same half plane of line AB, if the measure of angle ABD is less than the measure of angle ABC, then D is in the interior of angle ABC. Now I'm going to illustrate that with a couple of drawings. Now it might seem silly to make two separate drawings when the first drawing kind of gives away everything, but I think you'll see what I'm getting at. I'm going to go ahead and make both drawings. So there are my drawings. Now you can see that these are the exact same drawings that I drew earlier. The original unstated corollary had if this picture about the interior, then this picture about big and small angles. The theorem that we're proving now says if this picture about big and small angles, then this picture about a point being in the interior of an angle. So remember, I mentioned that the topic that we'll start out with is statements about big and small angles and points being in the interior of angles. Now the book does a proof by contradiction. I don't feel that a proof by contradiction is necessary, and I feel that it makes the proof harder to understand. I find it simpler to just prove the contrapositive. Let's go back up and look at the original statement. The original statement says, if the measure of angle ABD is less than the measure of angle ABC, then D is in the interior. The contrapositive says, if D is not in the interior, then the measure of angle ABD is not less than the measure of angle ABC. So the given stuff is still the given stuff. You have given points C and D in the same half plane. So I find it more straightforward to just prove this contrapositive. Now I've mentioned this idea before. I find often in books that I read that proofs by contradiction are used when a simpler proof by just proving the contrapositive is possible. So here we go. Suppose that in a protractor geometry, points C and D are on the same half plane of line AB. That is to say that D is in the half plane of line BA that contains point C. And also suppose that D is not in the interior of angle ABC. Well, if D is not in the interior, then either D is on ray BC or D and A are on opposite sides of line BC. This is by the definition of angle interior and by PSA 1. Let me draw these. So again, we're assuming that D is not in the interior of that angle. So D is not in that blue shaded region. Well, by PSA 1, D has to either be on that line or in that other half plane. So that's how we're able to articulate this OR statement. Now remember, when an OR statement shows up in a proof, you are set up to do a proof by cases. So those are the cases. This is one of the cases, and that's the other case. So case 1 is, suppose that D is on that ray. We're supposed to illustrate that. Well, that'll be easy. I'll copy that illustration and bring it down. Well, in this case, ray BC is the same ray as ray BD. So that means that the measure of angle ABD, now this is a typo, the measure of angle ABD will be exactly the same as the measure of angle ABC. So in this case, it is not true that that measure is less than the other measure. What about case 2? Suppose that points D and A are on opposite sides of line BC. We're supposed to illustrate that. Well, we've got an illustration. Let's go up and get it and copy it and bring it back down. So there's our illustration of case 2. Points D and A are on opposite sides of line BC. Well, in this case, we can say that points A and C are on the same side of line BD. Now that's using that theorem 4.4.8 up above. This theorem says that if this point is in the interior of that angle, then these points are on opposite sides. Or if these points are on opposite sides, then that point is in the interior of that angle. So that's the direction we'll be using. We know something about points being on opposite sides, and we're going to use that to say something about points being in the interior of an angle. So we are allowed to say that points A and C are on the same side of line BD by theorem 4.4.8 in the direction 2 implies 1. So let me illustrate that by pulling down that drawing and adding those points. Now I don't need to add points, I just need to change the half planes that I'm referring to. So I no longer need these half planes, and I no longer need that ray, but I do want to have a ray going through D. So there's an illustration of the fact that A and C are on the same side of line BD. So therefore, C is in the interior of angle ABD. And so that same illustration will work. And so that means that the measure of angle ABC is less than the measure of angle ABD. So that's by that unstated corollary. Now how can we illustrate that? Well, let's just copy this drawing, bring it down. Now let's get rid of this shaded interior and draw our two angles. So we just have this statement that angle ABC has a smaller measure than angle ABD. And so therefore, the other inequality is false. Measure of angle ABD is not less than the measure of angle ABC. Well, since this is what happens in both cases, we can say that this is true in all cases. And that's what we were supposed to prove. We were supposed to prove that the measure of angle ABD is not less than the measure of angle ABC. And that's the end of the proof. So we proved that if D is not in the interior of the angle, then the measure of angle ABD is not less than the measure of angle ABC. And the reason we were proving that was it's the contrapositive of this theorem. If the measure of angle ABD is smaller than the measure of angle ABC, then D is in the interior. So compare my proof to the book's proof by contradiction. I find mine a little bit clearer. Let's go on. We're going to discuss now the linear pair theorem. First of all, the definition of linear pair. To say that two angles form a linear pair means this. The two angles can be labeled ABC and CBD with B between A and D. So that's a picture of two angles that are a linear pair. Now the linear pair theorem says in a protractor geometry, if angle ABC and angle CBD form a linear pair, then the measure of those two angles add up to 180. Now let me illustrate that. So in the left picture, I just have a picture of a linear pair. In the right picture, I have a picture of two angles and the statement that those angle measures add up to 180. Notice that in my right drawing, I didn't do this. Why? Well, because ABD is not an angle, and angles can't have measures of 180. So I have to illustrate it this way. I just have to have a written statement that alpha plus beta equals 180. So notice that this is not an application of angle addition, because in our geometry, we cannot have straight angles, and we cannot have angles that have measure 180. So this theorem is not the angle addition axiom at work. This is something different. This is a theorem that you have to prove. Now I want to comment here on the use of the word supplementary. In the book, the word supplementary is defined as follows. Two angles are said to be supplementary if their measures add up to 180. So then the book states the linear theorem in this way. If two angles form a linear pair, then they're supplementary. I don't find any advantage to using the word supplementary. To me, it's just an unnecessary extra layer of notation. If you read that, then you've got to know what supplementary means and put that in your head instead of the word supplementary. I find it simpler to just say, if the two angles form a linear pair, then their measures add up to 180. Now the proof structure is this. Proof part 1, prove that alpha plus beta less than 180 cannot happen. Proof part 2, prove that alpha plus beta is greater than or equal to 180 cannot happen. And so therefore, alpha plus beta has to equal 180. Now, I will expand and justify and illustrate the book's proof of part 1 in this video. You will expand, justify, and illustrate the book's proof of part 2 in your homework. Now here's the book's proof of part 1. I've just typed this right out of the book. Notice it actually has some justifications. By this theorem, but here there's a key step where it says why is something true. But notice that there is not much space in this proof. In fact, they have some run-on sentences. For instance, here's a statement that's continued right along with another statement. And then here's another statement that's continued in the same sentence with another statement. I find it very important in math to only make one statement at a time. So that's what I mean when I say that I'm going to expand the book's proof. I'm going to separate statements that are combined into separate statements, and then I'll justify and illustrate. So my proof is going to be this content, but just expanded, justified, and illustrated. Now, in my expanded proof, statements and justifications that I've added are in boldface. So you can see there's quite a bit of stuff here that was not in the book's proof. So again, this is a proof of part 1. Suppose ABC and CBD form a linear pair, and let measure of angle ABC equal alpha and measure of angle CBD equal beta. And I'll add this illustration. Statement 2. We know that alpha plus beta is greater than 0. Why? Well, because angle measure addition axiom says that angle measure is positive. So if I add two positive numbers together, I'm going to get a number that's greater than 0. That's not stated in the book's proof. That's why I have it in boldface here. Now, suppose that alpha plus beta is less than 180. That's an assumption for a proof by contradiction. The book doesn't say this, but it's important to think that, and I think it's important to write it when you write a proof. Well, statement 4 says there's a unique ray BE with E on the same side as C. This should say the same side of line AB, such that the measure of angle ABE is that number alpha plus beta. Well, let me illustrate that. So there's an illustration of statement 4. The angle construction axiom says that this ray exists that creates an angle of that measure. Notice that when I cite the angle construction axiom, the book cites the angle construction axiom, that's all they say. I actually say how we use it. It's applied to ray BA and this given half plane and this given number alpha plus beta. Statement 5 says, observe that C and E are on the same side of line AB. Why? Well, we know that C is in this half plane, and we also know that E is in this half plane. We know that E is on the same side of line AB as point C. And also notice that the measure of angle ABC is alpha, and the measure of angle ABE is alpha plus beta, where beta is greater than 0. So the measure of angle ABC is alpha, and the measure of angle ABE is alpha plus beta. And so therefore we can see that measure of angle ABC is less than the measure of angle ABE. I'm going to illustrate that. There's an illustration of this statement that the measure of angle ABC is less than the measure of angle ABE. Now this statement was not made in the book. It's one that I added. That's why it's in bold. Statement 6 says that point C is in the interior of angle ABE. I'm going to add an illustration here. I'm going to illustrate this before justifying it. Now the justification for that is by Theorem 5.3.1. Now let's go back and look at that theorem. Theorem 5.3.1 says if you have 2 points that are on the same side of a half plane and one of them makes a small angle with ray BA on the edge of the half plane and one of them makes a big angle, then we can say this about one of those points being in the interior of the other angle. So that's the justification for this statement, and here's an illustration of that statement. So therefore, measure of angle ABC plus measure of angle CBE equals the measure of angle ABE. So I'll add an illustration of that. Now this is by angle measure axiom 3. There's a typo. The angle addition axiom applied to this situation. Now you can see that these words are in bold. The book doesn't mention that justification. Now I can therefore get this equation, alpha plus the measure of that angle equals this number. Now I just simply substituted in angle measures from statement 1 and statement 4 into equation 7. So in statement 1 we said that the measure of angle ABC is alpha. In statement 4 we said that the measure of angle ABE is equal to this number. So now if we do arithmetic, we can say that the measure of angle CBE is beta. There's an illustration of that statement. Let's go on. Statement 10 says that E is in the interior of angle CBD. Now why? Well, let's start by illustrating this. So there's an illustration of that statement, that E is in the interior of angle CBD. Now how can we justify that? Well, first of all, let's go back up and look at a previous picture. Notice we have this picture, that C is in the interior of angle ABE. Now let's look at our current picture. Our current picture involves some of those same points but a different shaded half plane. Well, let's go back up and look at Theorem 4.4.9 because it's about this same thing. Theorem 4.4.9 has pictures just like that. If we have this configuration of points, we can think about this half plane and this half plane and make these two statements. So therefore, we can say statement 11, that the measure of these angles add up. Let me illustrate that. So the angle addition axiom tells us that x plus y equals z in this picture. Now we can substitute in the known angle measures and get this equation, that beta plus that angle measure equals beta. Now we can illustrate that, just bring down the illustration from above. So we have this kind of goofy situation where we end up showing that this angle has measure 0. But statement 13 is impossible. It contradicts angle measure axiom 1, which says that angle measure has to be positive. So therefore our assumption way back in statement 3 was wrong. That's back when we said that suppose alpha plus beta is less than 180. So we see now that alpha plus beta less than 180 cannot occur. So that's the end of proof part 1. Remember the proof structure. Proof part 1 is prove that alpha plus beta is less than 180 cannot happen. Now in your homework, you'll expand, justify, and illustrate the book's proof that alpha plus beta greater than 180 cannot happen. And so the conclusion will be that alpha plus beta has to equal 180. That's the proof of the linear pair theorem. Now I want to talk a little bit about converse statements that are also theorems. Now remember from earlier in the video and from previous videos that when a theorem or axiom has the form of a conditional statement, the converse statement is not automatically true. If the converse statement is true, then it constitutes a separate theorem, and it has to be proved. Well, it turns out that the converse of the statement of angle measurement axiom 3, that is, angle addition, is true. The converse statement is presented in the book as theorem 5.3.3. So here's the theorem. It's the statement of this theorem is the converse of the statement of the angle addition axiom. It says this: in a protractor geometry, if the measure of angle ABC plus the measure of angle CBD equals the measure of angle ABD, then C is in the interior of angle ABD. Let's illustrate that. So notice these drawings of the reversed drawings from the angle addition axiom. The angle addition axiom says if you have a point in the interior of an angle, then the angle measures add up. The converse statement is if the angle measures add up, then that point is in the interior of that angle. Now the proof of this theorem is comparable in difficulty to the proof of the linear pair theorem. It's proven in the book, but I won't discuss the proof in this course. We'll just accept the theorem as given. Now it also turns out that the converse of the statement of the linear pair theorem is also true. The converse statement is presented in the book as theorem 5.3.4. It says this: in a protractor geometry, if the measure of angle ABC plus the measure of angle CBD equals 180, then B is between A and D, and so the angles form a linear pair. So I'll illustrate that. So there's the statement of the converse of this statement of the linear pair theorem, and that's a theorem. Now you'll justify and illustrate a given proof of this in a homework exercise.